Okay, so again, we're just going to continue with 2.3 today. I said we're going to do a few more of these algebraic methods for solving limits. And then we have another technique that we haven't mentioned yet. That's kind of a fun one. I think it's fun. Yeah, that's me. So let's go over each of these. So let's look at number one. What happens if we try to do an algebraic? So we're not graphing. We're not going to sit and make a chart. We know that's very tedious, the chart. And we can't always just pop everything on a graph, especially during a test. So if I try to just plug in 1 automatically, what do I get? I get zeros in a denominator, right? That's not going to work. So I have a subtraction here. How do I subtract two rational expressions? Because that's what these are. These are rational expressions, meaning fractions. How do I subtract them? Well, how do you subtract any fraction? Yeah, you need a common denominator. To get a common denominator, the best thing is to have each denominator in its fullest factored form. Do we have that yet? So we can factor, I'm just going to do it right underneath, x squared minus x, right? Well, how do I factor x squared minus x? Pull out. All right, so now it's easier to get our common denominator. We're very close. We have an x minus 1 here, right? Oh, we have an x minus 1 here. They do have something in common. That's good. But what extra is over here? An x. So what do we need to do? We got to get that x to appear over here, correct? And I can do that as long as I also stick it where? In the numerator. Because what is x over x? 1. And I can multiply anything by 1. 1 is going to look like infinitely many things. So by multiplying it by x over x, I didn't change the value of the expression. What I allowed myself to do is say, hey, now I've got this common denominator. This is x times x minus 1. And now this is x times x minus 1. So I can bring them together. Now, a little bit about notation. You see the limit out front? Until we plug the number 1 into the problem, that limit stays there. Do not leave it out, especially on a test. So this equals the limit as x approaches, and you don't get to leave out the x approaches 1 either. You take the time to write that, okay? So now I have this common denominator of x times x minus 1. And what do I have in the numerator now? 1 minus x times 1, right? So we see it's 1 minus x. Okay. Well, does 1 minus x cancel with x minus 1? So there's a lot of manipulations you got to do. But they're all mathematically legal. As long as they're mathematically legal, you can do them. I cannot cancel 1 minus x with x minus 1, correct? They're not the same. But I can turn the numerator 1 minus x into x minus 1 by doing what? Anybody remember? You're going to make a much more complicated problem. I'm going to come up with something even quicker and simpler. How's that? You can factor negative 1 out of any algebraic expression. What does factoring a negative 1 out? So let's take a look. I can factor negative 1 out. So again, I got to keep the limit. And I'm going to pull negative 1 out of here. When you pull out a negative 1, all it does is flip the sign. So that means this positive 1 becomes what? Minus the negative 1. And minus x becomes positive x. So now I have negative 1 plus x. Well, negative 1 plus x can be written as how? Yeah. Now, can I cancel my x minus 1s? Absolutely. So what does this limit look like after I did my algebra manipulations? It looks like the limit as x approaches 1. What's left over here? Just my -1 over x. And guess what? This expression, -1 over x, is the exact same thing as that big expression up there. Yeah. Way back when you took those algebra courses, whether you did them in high school or you did them here at RVCC, or you did them at another college, your teacher might have said, one day you're going to need all this for calculus. Yeah, they weren't lying. You need it all for calculus, okay? So again, I try to review things as we go along. Can I plug 1 in there and get something that works? Absolutely. The second I plug the 1 in, I no longer need to write the limit. So the limit as x goes to 1 of 1 over x squared minus x minus 1 over x minus 1 simply equals -1. And when you're trying these on your own, what is the best way to test it? You're practicing, because you're going to practice a lot of calculus on your own, right? The best way when you're practicing it on your own is have Desmos open, type that whole crazy thing into Desmos, and look at the graph. Look at what's happening as your x goes to 1, okay? And you'll see it. All right? I'm going to take number 2 and put it underneath of there because I'm not going to have enough space on the side. Let's look at number 2. Number 2 was, put it here. Okay. Start by just plugging in 0. What sign is 0? Without a calculator. You can do sine of 0 without a calculator. Sine of 0. Everybody? We're going to wake up. What's sine of 0? 0. Yes. Remember I said, probably don't bring markers. Here we go. Remember I said one of the best things is just to know your sine curve, because then you can visualize it. Oh yeah, sine of 0 is 0. All right. So if I try to plug in 0, I actually get, well, okay, what's sine of 2 times 0? Still 0, right? Because what's 2 times 0, everybody? 0. Sine of 0, 0. So I get like something crazy like that. We can't use that. This goes to our trig identities. I will tell you right now, this is one of the most common ones. Know it, memorize it, use it. All right? There is a trig identity. Way back when you took Pre-Calc 2. Some of you, I think, were with me over winter session, so that wasn't that far back. That was like 2 weeks ago. Know this. I'm going to put it bright in red. Sine of 2x is the same as 2 sine x. Okay, you do not need to go and memorize every trig identity. But there are going to be ones we're going to use a lot. This is one of them. Know it. Okay, Pythagorean identities. Know those two. We'll come across those at some point. Oh, well, it's a trig identity. That means I can rewrite this limit and instead of writing sine of 2x, I can write 2 What does that allow me to do? Take out your sine x. Boom. Ba-bum, ba-bum. Rewrite your limit. So what you're seeing me do in class are hints what I kind of expect to see on a test. You know, I don't give a lot of problems on the test because I want you time to take them. I don't want you to feel rushed. You want to show as much work as possible so I can give you partial credits if possible. Remember that. All right, so this is the limit as x approaches 0 of just what? 2 cosine x. Now I can plug it in. It equals 2 cosine 0. Well, if that's the sine graph, visualize the cosine graph without a calculator. Tell me what cosine of 0 is. 1. Cosine of 0 is 1, so it's just 2 times 1, and the answer is 2. That's a good one. Know it. The third problem. Number 5 plus x. You're going to have to remind me what it was. The third one. It was 1 minus 1/5 over x. Okay. Thank you. I hope you can see if you just try to plug in 0, you got some issues going on, right? You got all kinds of issues. You end up with 0 over 0 again if you plug in 0, right? Because you're going to have 1/5 minus 1/5 is 0, and then you got 0 in the denominator. We can't do that. But we have a complex fraction. How do we make a complex fraction not complex? So I'm going to choose, there's always different methods. You can take the time to subtract the numerator, and then you can do division by doing multiplication of reciprocal, or you can just kind of do it all at one shot. That's the method I like to use. And to do that, I find my denominators, not the x. I find the little denominators. In other words, if I can clear out 5 plus x and 5 from the problem completely, I won't have a complex fraction anymore. All right? So, well, there are two different denominators, right? So the common denominator for this particular for those two up there will be 5 times 5 plus x, right? Does the x value have a denominator? No. Does everybody see that? If it did, we would need to use that too. But it doesn't. So it's just x. So one way to do it is just go ahead and essentially, it all goes back to the number 1, right? Everything goes back to the number 1 because I can multiply by the number 1 and it doesn't change anything. So the number 1 I'm going to use is I'm going to multiply the numerator and the denominator by that common denominator. Oh, it's 5 plus x, x plus 5, same thing. Okay? 5. Because 5 times x plus 5 over 5 times x plus 5 is simply 1. And look what happens when you distribute in the numerator. When I take this and multiply it by that whole fraction, what's going to cancel away? The x plus 5s, right? And what am I left with? I'm left with 5 times 1. Okay? Then I'm going to do the same thing. I'm going to take this and I'm going to distribute it to here. What's going to cancel? If I take 5 times x plus 5 times 1/5, what cancels? The 5's cancel. What am I left with? Yep. Be careful with the sign. Notice the use of parentheses. The numerator gets a little messy. It's actually 5 times x, right? Oops, I don't need a parenthesis there. It's 5x times that is how you take a complex fraction and make it not complex. What makes it not complex? There's no fraction inside a fraction anymore. There is no fraction inside a fraction. We can clean that up. We can easily clean that up. First, keep the limit. We're still using the limit. All right, I'm going to clean it up here. What is this? This is 5. Distribute your negative. Biggest mistakes is forgetting to distribute a negative. Minus x minus 5, right? So what does that end up being? What does my numerator come out to? Going. Negative x. You see a pattern here? The part of the denominator that's been causing us the issue in all these problems ends up getting canceled away. Everybody see that? Because what can I cancel now? The x's. I still have a limit. Don't forget, you still got a limit. As x goes to 0 of, what's left in the numerator? Negative 1 over 5 times x plus 5. Now that I have this simplified version of my complex fraction, go ahead and plug it in. And then what's the answer? Negative 1 over 25. Okay, in all of these cases, what was causing us the issue of not being able to evaluate the limit from the beginning, right, ends up getting canceled away in the problem. Even when we factored, remember the ones we did on Thursday where we factored, it got canceled away. When you graph these, the same phenomenon will happen on every single graph. If the piece in the denominator that's causing the issue goes away, all right, we do have a limit at that value A. In this case, it's 0. We've got a limit. Our graph from the left and from the right is going to negative 1 over 25. But what occurs at exactly 0 on this graph? I mentioned it in Thursday's class. When something in the denominator cancels away, you can still have a limit. But on the graph itself, there's nothing there to evaluate it. What's on the graph? A hole. That's important to remember, especially as we get into the lesson we're going to do in 2.4 after we do the next technique. When it cancels away. So when you look at Desmos, you're not going to see a hole. You're going to see a smooth curve. Until, remember, I put my finger on it, and you go to 0, what's it going to say? It's going to look like it should be at negative 1 over 25, but it's actually going to say undefined. Not the limit. The limit exists. But the function itself is undefined at that point. There's a big difference there. Okay? So that's our algebraic. Those 3 problems I just did, for those of you who looked at the lab, will really help you with those problems on the lab, okay? So you'll be able to practice similar problems as you're finishing that lab. Okay? Now, there's one last technique that doesn't come from, it's a specialized algebraic technique, we'll call it, all right? So we know we can graph, we can do numerically, we can just plug a bunch of numbers in, very tedious. We can work algebraically. There is kind of a special algebraic method that I want to take a look at. And the best way to do this is probably to go to Desmos. So if you can pull up Desmos, I'll pull it up on here. And I want to this time I want to start off by actually graphing the function. And the function I want you to graph is x squared times sine of 1 over x. All right, so I'll write it here. X squared Okay, that's the function I want you to graph. So let's get on Desmos, which I hopefully can do quickly. You should be able to get on Desmos somehow and graph that. All right, so it's x squared. Sine of 1. Okay, so you got to figure out, that really doesn't show you much, right? So you got to learn to work with windows in Desmos. There's different ways to do it. I have a touch screen, which I love, because I can just zoom, zoom like that. If you don't have a touch screen, you need to go to this little wrench. You see the little wrench? And you got to adjust. You want to really bring it down. You probably want to go from, like, for the X, try -1 to 1, and even for the Y, try -1 to 1. Do something like that. If you don't have a touchscreen, if you have a touchscreen, you just kind of get to go like, yeah, right. You get to go like this if you have a touchscreen. There we go. Wow, look at that function. Okay, so play around with Desmos. Actually, no, you got to go even further. To really see it in Desmos, if you don't have the touch screen, why don't you go from -0.05 on the X to +0.05, and then on the Y, you need to go from, -0.002 to +0.002. That's why I love touchscreens. I'm gonna make it. I guess it's all right. I'll leave it as it is. So, yeah, we're gonna be graphing some really, really crazy graphs in here. But what I want you to notice with this, and unfortunately, see, I want to be able to write. I can't write on Desmos. It's a little annoying. I can't just take my pen and write on it. But that's okay. Not everything's perfect. We can see. So ultimately what I want to do is I want to get a limit, right, as this approaches 0. Which, remember, graphically is easy. Everybody can see. As the limit approaches 0 from both sides, what's it actually going towards? Another 0, right? Isn't it going to 0? So as you approach from the right, as you approach from the left, and if I zoom in even further, which it doesn't, yeah, again, touch screens. All right, you can see it's getting to 0, right? Yeah, sine curves give you the most fascinating. If you start manipulating trig graphs, you get like some really cool pictures. Anyway, so it's fine. We can do it graphically. We know answer 0. We can see it on the graph. But how do we do it algebraically without knowing what the graph looks like? That's where it gets tricky. Because you see, you cannot just plug in a 0 into this function. Not going to work. It's definitely undefined at 0 itself, but the limit's approaching 0. So there is this fun little theorem, and it has 2 names. In our textbook, we call it, and I'll get to the notes and write it out in a minute, the squeeze theorem. It's also called a sandwich theorem. Now, here's what's happening. I was going to write on my, nope, I got it right up here. That's a problem. Isn't that a problem? That's a problem. Probably a very basic problem of x squared. It's a problem. It may not be x squared, but it's a problem. What's this? Oh, that's another parabola. Do you see how the function we created is squeezed between those 2 other functions? Everybody see that? So I'm gonna give you the theorem in a minute, but the idea is we've got a parabola on top, we got a parabola on the bottom. This is definitely sandwiched or squeezed between those two. So here's the idea. If the limit of the two functions it's being squeezed between is equal, in other words, what's the limit of the top parabola as it approaches 0? Isn't it 0? What's the limit of the facing down parabola as it approaches 0? Doesn't it go to 0? So the idea is if you can figure out what it's squeezed between, and they have the same limit, then the original function has to also have that limit. All right? That's the idea behind the squeeze theorem. Now I'm going to actually give you the theorem, and we'll look at it. How do we do that algebraically without knowing what the graph looks like? So let's take a look. Go back to the notes. And let's give you that formal theorem now. So let's see if it makes sense. Here's what the theorem's going to start the way everything else started. Assume the functions, but now I got to work with three functions, right? I've got the original function f, but then I've got the two functions it's being squeezed between, right? So I'm going to add a g function and an h function. So let's assume. And in our book, this is called Theorem 2.5, if you want to look it up in the book. It's called the squeeze theorem. So let's assume that the functions f, g, and h satisfy all right, they're putting g of x in the middle. That's fine. It doesn't matter. I'll do the same one that's in the book, so if you do look it up in the book, it looks exactly the same. So just write this out and we'll talk about this for a minute. Okay, so there's the squeeze. This is showing, hey, g of x is literally squeezed between f of x and h of x. That's what that statement says. All right? Function is in between those two. For all values of x near a, except possibly at a. Remember, we're just getting near our a value. It doesn't have to be at. Except at a. Okay, so here's the theorem. If the limit of f of x as x approaches a equals the limit of h of x, I'm going to move this up a little, as x approaches the same a, they both equal some value L. That's our y value, okay? So in other words, the f of x and h of x in the example we just did represent those two parabolas, right? So if those two parabolas are approaching the same limit, and we know g of x is in between the two of them, then we can conclude then the limit of g of x, that's a g, as x approaches a, also equals L. Okay? I really am trying to work on my handwriting. I promise. You have these notes. You're looking back on this. It's written all nice out, nice and neat. Prettier pictures. I think the graph we just did is on there too. Okay? So how can I do this one now, algebraically? Algebra manipulations. All right, let's go back to those. how do I get this function, x squared sine 1 over x, in between two other functions? All right? How we do this is you have to start with something you know. Now, so I want to do it for the limit as x approaches 0. So 1. Start with a known fact. Okay. Here's your known fact. Sine of anything where theta can be anything. It's just anything. All right, sine of anything. I want you to think back to this sine graph. Okay. Domain of your sine graph is all real. It could be anything. You can plug anything into a sine function. Doesn't matter. But think about your output. No matter what you plug into a basic sine, it will be restricted between, the answer's restricted between which two values, everybody? 1 and -1. So is it true, your known fact is, hey, sine of no matter what is that theta has to be between, y'all agree with that? Not x, sorry. Pretend that wasn't there. 1. Make sense? There's my known fact. I am now going to take this known fact and manipulate it to look like this. That's it. 2 steps. Second step. Manipulate the known fact to look like your equation. We're not going to do too much with squeeze theorem. So yeah, the problems you're going to be given are just a conceptual understanding, or you'll be given like a sine or a cosine, where they all start the same way. Does that make sense? I'm not going to give you something else where you got to come up with that known fact. Okay? So all the squeeze ones that you will do on your lab will either be conceptual, all right, or you will be given a sine or cosine function to work with. Okay? So it'll look like this. All right, so now I'm not working with sine of theta. What's my theta in this problem? It's not sine theta, it's sine of what? 1 over x. That's okay. Guess what? Sine of 1 over x also has to be between 1 and -1. Because sine of anything. So, yes. Manipulate the known fact to look like your equation. All right, so I've already started. I took the theta, replaced theta with what my theta actually is in this problem, which is 1 over x. Everything's still good. What else do I need to make it look like that? What's missing? X squared. That's okay. These inequalities are like equations. I can put an x squared here, and to keep it balanced, I just have to multiply the ends by x squared as well. Multiply this by x squared. Multiply that by x squared. So now it looks like this. Does this look like my original function now? You already know the graph, all right? You already know, does it make sense that it's being squeezed between a parabola that opens up and a parabola that opens down? Yeah, but remember, you're doing this without already seeing the graph normally, okay? You're going to go through this. So you're saying, okay, I'm being squeezed between -x squared and +x squared. So now I go to the theorem. What does the theorem say? I need to check if the limit as x approaches a of the one end equals the limit of the other end. That's what I'm doing right now. So let's do that. So step 3, apply the theorem. What does that mean? All right, let's do it. First, I'm going to do the negative x squared. What is the limit as x approaches 0 of negative x squared equal to? Oh, we can just plug that in. What does that equal to, everybody? 0. Cool. You got to do the other side. What does the limit as x approaches 0 of just x squared equal? Everybody? 0. Now, applying squeeze says, since the limit, the lower bounded limit equals the upper bounded limit, then whatever's in the middle, according to the squeeze theorem, I don't know why I wrote squared there, didn't mean to. According to the squeeze theorem, that also equals 0. Done. Okay? Will I ask you to do one of those on the test? Yeah, probably. Okay? They're not always going to be 0. Sometimes you'll manipulate it, and this will be a 1, and that'll be a -1. You do the squeeze problem you have on the first lab, which is due, you're working on the rest of today, after I do the next lesson, of course, is more conceptual. But next week, when you're just given a bunch of limits, this is a technique you will have to use on at least one of them. So you will apply a problem like this on next lab. Okay? So there's your squeeze theorem. Questions? Yeah. Yeah. So you can try squeeze on something, and if these two, the limit of your, in this case, it was our f of x and h of x, we put g in the middle, they don't equal each other, you're done. You can't apply squeeze. And here's what I'll tell you. Limits are a funny thing. We try all sorts of techniques. Sometimes the only method is just to graph it. Now, on a test, I would not give you that because you're not going to have a graphing tool. I can guarantee every problem I give you on a test will be done numerically or will be done algebraically. If I ask you to graph it algebraically, you'll be able to apply something. That'll work. So, for this particular problem, it is hard to know when to use squeeze. I would say when you have a sine or cosine function, and there's no other manipulation you could, like that particular x squared times sine of 1 over x, there's no identity that's going to help us there. Okay? There's nothing that can actually help us. Right. Yeah, if you have an identity that'll help you, you would do that. Yeah, I think when we're working on lab 2 of this unit, you'll start to get it because everything's kind of mushed together, and you'll be like, oh, okay. You'll know when you've exhausted everything. So let me try squeeze. When it starts to kind of work out and you get this nice balance, you're like, oh, wait a minute, it's going to work. You'll know you can use squeeze. Okay. All right. I'm going to stop this. So that is it for 2.3.